It's a pleasure to be here today. As you said, I'm Catherine Williams. If I'm not mistaken, this is the last talk of the day, which is appropriate in some ways because I'm going to tie together a few themes that we've heard earlier. I'm in the ad tech industry, as was the QuantCast speaker this morning, Peter. I'm going to talk a little bit about pricing, just like our previous speaker. And along the lines of what Ben was just talking about, I'm going to tell you a story. So my story is about bidding strategies for display advertising, how to avoid boiling the ocean. And I was told that this audience might appreciate, or at least wouldn't mind terribly, if I got a little bit technical. So it's going to be a technical, tactical story to end your day. Okay, so first let me introduce our protagonist. This is AppNexus, the protagonist. Here's our tagline. We provide the technology that empowers companies to buy and sell online advertising programmatically. So first and foremost, we're a technology company, and we enable and optimize programmatic buying and selling of online advertising. So our technology helps advertisers to make the most of their campaigns, publishers to make the most of their inventory, and ad tech companies, which are built on top of us, to make the most of their data and insights. And this all sits on top of our cloud-based software platform. Okay. One more standard marketing slide about our protagonist, AppNexus. I think some of these numbers are a little out of date. We are the scaled independent leader in this space. Scaled in the sense that we operate at global internet scale. We've grown year over year enormously. That's actually going to be an element of our story. We serve, I think our high water mark was around 3 billion ads a day. We process an enormous amount of data, and we receive an enormous number of inbound queries per second. We're privately held. We've received venture capital funding from a variety of partners, as well as some from strategic partners, including Microsoft and WPP, which is the world's largest agency holding company. We have a global footprint and over 1,000 employees. So scaled, right? Now, independent might be more interesting, so I just want to point out briefly the two juggernauts in our space, the two other internet scale advertising platforms are Google and Facebook, both of which have B2C, like consumer-oriented products and services, as well as their own properties, their own inventory that they monetize via advertising. So we're independent in the sense that we're agnostic. We don't own any inventory that we monetize, and we're completely anonymous, or at least users are completely anonymous on our system. Okay, so there's our protagonist. Now, fortunately, our first speaker this morning talked a little bit about real-time bidding already, so I'm not going to have to belabor some of these points. But this is the bread and butter of the AppNexus platform. So for those of you who are not familiar, here's a little diagram. When you, user, little red faceless user, go to a browser and load up a web page, each one of those ad slots calls out to a platform like AppNexus, it may be AppNexus, and requests ads. AppNexus then holds an auction, or submits out bid requests, actually, from different advertisers that are integrated with our platform, requesting bids for those ad slots. We hold an auction. The highest bidder gets to send their creative, in this case I think it's a hamburger ad, back to that ad slot, and this all happens in less than 100 milliseconds. Okay, so this blew my mind when I first learned about it about, 3 years ago, but I think everyone here is probably more savvy than I was then. So just to be really crisp about our definition here, an ad impression, then, is a creative served to a single user at a single point in time via a browser or a mobile app or what have you. So if you hit refresh on your browser, you're going to see a whole new slew of impressions. It's one instance. Okay. Now, because there are so many of these, based on people's web surfing habits, even though they transact individually, we price them and think of them in terms of thousands. So you'll hear CPM, cost per meal, cost per thousand later on. Okay, now there are many interesting stories that I could tell about data science at AppNexus, and their adventures and dragons and what have you. But today's story, I'd like to focus on some of our core platform logic. So in particular, let's start with a little auction theory. Okay. A Secondprice, or sometimes called Vickrey auction, is a type of sealed bid auction. Bidders submit bids without knowing the bids of the other participants in the auction. An independent third party then reconciles the bids, says who's the winner. The highest bidder wins, but importantly, pays the second highest price in the auction, maybe plus 1 cent. Now, one thing that makes this, AppNexus runs a second price auction, as do many other ad exchanges. One thing that makes this so beautiful and so elegant, the reason I'm mentioning it, is because it lends itself to a very elegant and natural bidding strategy. So here's a little bit of math for you, some game theory. Suppose we have n bidders in an auction. Say the ith bidder bids VI for an impression, or so rather that's its value for the impression. We're assuming that each individual bidder has their own valuation of that object. This is where I'm tying into the car talk that we just heard about, because I am assuming here that bidders know how to value those impressions. I'll get to that a little bit more later. Okay, so our bidder values the impression at V, but they bid B. Now we say that the auction is truthful if their bid is equal to their value. Makes sense, right? So their payoff then, well, they're going to get no payoff if they don't win it. If they do win, the payoff is the difference between their bid and the price they pay, or rather their value and the price that they pay. That's their margin. So one can prove that in a second price auction, at least a single second price auction, the bidder optimizes payoff by bidding truthfully. And I'll leave that as an exercise for the audience because it is actually very easy to prove. We can talk about it afterwards. But that's very elegant, right? So now the problem of bidding in a second price auction just boils down to how do you value the impressions in the first place? So here's the valuation problem. AppNexus does this on behalf of clients who integrate with us directly if they choose. They may have their own valuations or they can use ours. So our job then is to algorithmically determine the value of each impression in real time on behalf of a buy-side client. Now, in order to do this, they need to have something that they're measuring. So I think the phrase direct response advertising was used earlier. We're usually looking for a click or a conversion that can be measured via a pixel or some other sort of event that you can measure, right? Okay, and so the advertiser usually has some revenue number associated with that. They'll pay $10 for a lead or $1 for a click, or if somebody actually buys something on an e-commerce website, maybe that's worth $100 to them. Okay, so then our job just becomes, we need to measure the expected value of, the expected revenue rather, of that impression based on that goal, which is then just the probability of the event occurring that generates that action or that revenue times the value of the revenue times 1,000. There's that 1,000 from the CPM units again. Okay, great. So how do we then predict that probability? Well, there are a large number, again, as we heard this morning, there are a large number of features that we could use. Every one of these ad impressions has a huge number of features associated with it, and some are more predictive than others. Anything ranging from features of the ad itself, like what is the actual image, what is the size, bigger ones can have a higher impact. What is the domain or app that the ad is showing on? Where's the geography of the user who's seeing the ad? Now we know that ISP geolocating is not necessarily good because we're apparently in Kansas right now, but in general this is a pretty good signal. Creative recency and frequency, turns out people get creative fatigue. If you see the same creative over and over again, you're less likely to react to it. So that's something we need to measure, how recently they've seen it. And a wide number of other features as well. So you see them on the list here. Now, the core AppNexus algorithm that's been in place for a number of years is just the orange ones. So I'm going to focus on those going forward. But there are many, many features. And I guess let me just note also user ID and user segments. That's all the demographic data that Peter was referring to this morning that can be used and is highly predictive if you have it. Okay, so I think this is the mathiest slide I've got. Let me just tell you, how do we actually put this data into practice to make some sort of a prediction to create a bidding strategy? So this is the AppNexus way that it's been done historically for several years. First of all, we cluster the world of inventory, the sea of inventory, into similarly performing slices. So this is going to involve domain or app and geographical region, among other things. These are called venues. These need to be roughly the same size and big enough to see a large volume of data. Then an optimization node is a 3-tuple, or in particular a buy-side, sell-side pair of campaign creative, that's buy-side, by venue on the other, and we're going to make a prediction per combination like that. So for each one of these buy-side, sell-side pairs, our prediction then is given by this formula. Now, I don't want to belabor the actual notation here. The point is that we create a probability distribution based on what we think the true event rate of this buy-side, sell-side combination is going to be for some given event. Say it's a conversion, right? And we're going to try to estimate that based on both whatever data we actually see for that campaign creative on that venue. So that's our capital N and our little x. So that's the actual observed data, as well as some sort of prior, some sort of Bayesian prior that we're going to make based on higher level historical data. I'll say more about that in a second. So when you start out, you have no data, right? Your x is 0, your n may be 0. So you're going to rely very heavily on this prior probability. And then as you gather more and more data, the posterior probability will shift to the actual, and in the long term, it'll converge to x over n. We then look for the max likelihood of that posterior distribution, and that's our prediction. Okay, I promise that's the mathiest thing in this, this deck. Now, what informs that higher level data? Well, remember, this node that I was just talking about is a specific campaign, a specific creative against a specific venue, which is a specific slice of inventory. So that's very granular. So the higher level data is just coarser aggregations. I'm not going to belabor what the exact hierarchy of these different aggregations is, but it can include data aggregated at the member level. This is like the buyer member level, or the advertiser level, or the publisher level, or brand, or content category, or even second order combinations of these, but they're going to be coarser than the node. So basically, we warm start the prediction problem by calibrating our Bayesian prior based on the data from the most granular, higher level data, most granular, higher level set that has sufficient data, and then we're good to go. Okay, so to summarize, we now know how to bid in these online auctions. We know how to start from 0, use a Bayesian prior based on higher level data, and then wind up converging towards an accurate prediction, so an accurate valuation, therefore an optimal bidding strategy. No problem, right? We just go off and apply this algorithm and bid across the whole ocean of inventory and we'll be fine. Here's where our protagonist meets conflict, and we introduce the boiling the ocean problem, also sometimes known as the peanut buttering problem. So what do these two metaphors have in common? Well, as I mentioned at the beginning, AppNexus has grown enormously in the past several years. So when this algorithm was first designed, it used to be that you could bid on all available inventory and quickly ramp up, get more and more data, and eventually get accurate predictions. But as we brought more and more inventory onto our platform, now the same campaign is spreading, so peanut buttering, its learning impressions across a huge sea of potential domains and what have you, right? And it makes it harder and harder for it to get those accurate valuations quickly. Or you might say trying to boil the ocean with a little lighter. I've never really been clear on exactly how that metaphor works. Okay, so just to be really concrete here, let's just look at some numbers. Suppose we have a campaign, just to be simple, with 2 creatives buying on 5 venues, so that's 10 nodes, right? So this is in the old world. Suppose that these venues, or rather these nodes, have a 1 out of 200,000 conversion rate for some conversion. That's actually a realistic and good conversion rate for some sort of like e-commerce shopping thing. Suppose the campaign buys 20 million impressions. That averages about 2 million impressions per node. And so again, on average, roughly, we have about 10 conversions per node. That is pretty good. That is enough that we're going to be able to come up with a reasonably accurate valuation pretty quickly. If some of those nodes are not as good, we'll get to 0 pretty fast, all as well. But now, once the inventory ocean expands and becomes very, very wide, we have, say, 500 venues that this campaign is targeting that just meet its targeting criteria, right? All of a sudden now we have 1,000 nodes. That same 20 million impressions that the campaign was willing to spend to learn or to get started now gets spread out to 20,000 impressions per node with on average 0.1 conversions. That is to say, on average, most of these nodes have no conversions whatsoever. So we have nothing. So we're still bidding using our prior higher level distribution, and just wasting money. So this is exactly what happened. Clients saw that their campaign dollars would go and go and go into what seemed like a black hole to them, and they wouldn't start getting the positive results. So what seemed like a good thing, having more and more inventory available to them to be able to find users, actually became a very, very bad thing. All right, so here's the climax of my story. Our solution. A little bit of foreshadowing, because there's going to be a toe dipping into water. Their solution is to focus the spend. Now, like a bad mystery, you probably saw this coming, right? You're probably thinking, like, I bet I know how to solve this. Here's how we solve this. First of all, we're going to use that same higher level data that we talked about for calibrating our prior before, and now we're going to use it to rank inventory slices in advance. Now, previously I was talking about venues. Now I'm talking about a system we built more recently, and we've moved away from venues. So I'm just going to say generally inventory slices. But we're going to use that higher level data, whatever historical data we have on the platform, to predict the performance on these inventory slices in advance of a campaign actually running. And we're going to rank them. Now, when a campaign starts, instead of bidding everywhere across all the possible inventory that passes targeting, we're going to have it bid only on the top inventory slices, depending on whatever its targeting it is, and then in descending order. Now, stage 4, we'll quickly test. We're not just going to let it go and go and go. We'll quickly test to see whether or not that's going to be a good inventory slice for it, and discard it if not. Number 5, we'll then move down the list so that we target or allow it to bid on the next most highly ranked inventory, and wash, rinse, repeat. So in the steady state, the campaign is achieving 100% of its daily delivery goals on what we know is the optimal inventory, because we start at the top of the list. But of course, since this is a little bit of a multi-arm bandit problem, exploit, explore, we're going to continue to explore the space as well. So broadly then, these fall into 3 main components. These literally map to components in the back end in our system. The first one is ranking. The second one is toe dip. So this is my affectionate term for it. Properly speaking, it's called the quick test, but I still prefer toe dip. And then the third component that glues it all together is the control system. So as the denouement of my story, I guess, I'd like to tell you a little bit more about the ranking system and the toe dip system, which is my favorite part, and then see if you have any questions. So the ranking, I didn't include technical details here, but the basic idea is that we're going to employ standard machine learning techniques and that higher level data that I've been referring to predict the probability per inventory slice. Now here, we also call them sell-side keys, so my terminology is getting peanut buttered. We use these predicted probabilities then to rank the slices. So here on the right, you see a potential list of sell-side keys or inventory slices ranked. Now, because remember, there were a whole bunch of different features we could have used as our higher level or coarse aggregations, we carried out some feature selection. This was actually a pretty interesting process. So we used logistic regression with L1 regularization to choose which features would be most predictive, right, of these higher level ones. And it turned out, it was pretty interesting. App and domain, very predictive. Brand country group combinations. Apparently some brands work very well in certain country groups, or at least that combination is meaningful. And brand category, content category combinations wound up being very predictive of how well a campaign would do. So with those 3 features selected then, now each one of those is actually a categorical variable, and they have very, very high cardinalities. So apps and domains in particular have like tens of thousands of values on our system, if not even hundreds of thousands. So we have to be a little bit careful here. So what we do then is take these categorical variables and then translate them into the actual event rates that we see on those individual categories and plug the numerical value into our regression. So at the end of the day, we have a standard logistic regression on these 3 features that we use to make our prediction. What's lovely about this is that when we were doing the valuation problem and creating that prior distribution, we knew it wasn't accurate, and it mattered, because when you're pricing, accuracy matters a lot. But here, it's just the relative probabilities that matter. We're just ranking, and so the inaccuracy, not such a big deal, because the relative ranking comes through. Okay, enough about that. I will say we use coordinate descent in the actual implementation, but okay. And so then finally, the toe dip, my favorite part, partly because I was there when it was born. the basic idea here is that we're going to metaphorically dip our toe into the water of each inventory slice, see whether it's good. If it's not good, pull our toe back out. If it is good, dive in. So less metaphorically, for each campaign, we're going to start bidding. If we receive an event on that inventory slice for that campaign, great, dive in, keep going, it's done, it's passed. However, if we keep bidding and bidding and bidding, and it doesn't receive an event, and the probability that that node, that is that campaign inventory slice combination, is good, drops below lambda, where lambda is some threshold value, then we're going to stop bidding. So we're going to bid until the probability that it's good drops below lambda. Now, again, we're going to use a Bayesian prior here. Here it's going to be an uninformed prior. But the point is, lambda now is the tolerance for mistakenly rejecting good slices. So if lambda is very high, we're going to be very aggressive. It's going to be a very quick toe dip. If lambda is low, we're going to bid for a long time before we decide that we're just not going to get an event. We're going to throw it out. So we can control that. And it's straightforward to compute what the maximum n is for a given lambda. I mean, it's just some calculus. Our goodness criterion for a node is typically a minimum conversion threshold. So for the ranges that we usually see on our platform, we wind up with n in the low tens of thousands range. So this is great, right? We can quickly, within like tens of thousands of impressions, decide whether or not a given inventory slice is worth spending on. And if it's not, just toss it out and move down our list of potential keys. So here then, let me just sort of graphically show you the control system at work. Let's suppose here on the right that we've put the first 4 keys in to bid. The first 2 passed, the third one failed, the fourth one passed. So the 1, 2, and 4 on that list keep bidding. We add 2 more from our control system because we don't have quite enough delivery. 1 passes, 1 fails. We add 2 more, et cetera, until we've gone through the whole ranked list and we have sufficient delivery, and it's all the best inventory for this campaign. So in the end, you see the protagonist wins because it figures out how to boil just enough water for tea and not spread the peanut butter too thin. Thank you.